So let me just kind of give you the upshot of how the impulse response tells you about the LTI system properties. So the first property we're interested in is memoryless. And the result is that S is memoryless if and only if. So this is a necessary and sufficient condition. If and only if the impulse response, well, basically what it tells us, it's a pretty boring system, is the impulse response is just a scale of a unit impulse. So really the only memoryless linear time invariant systems are basically gain control. That's it. Those are the only memoryless ones. The second one, actually, I'm going to do them slightly out of order here. Well, that's all right. I'll just do it here. It'll fit. So what about invertible? How do we tell whether or not the system is invertible? Well, S is invertible if and only if there exists, and I'm going to express it again in terms for discrete time systems, but we're going to see that all of these will be analogous for continuous time. If and only if there exists a G of n such that H of n convolved with G of n is delta of n. And one way to kind of visualize this is through this kind of a serial concatenation. Let's suppose we had S. This is kind of actually a proof of one direction of that. Suppose I knew that the system was invertible. So this is showing that invertibility implies this. Okay, so this is showing that this is a necessary condition. If I had an S, and then I had another system, S tilde, which inverted it, then what I know is that when I put xn into this S, and then put the output of that into S tilde, since it's the inverse, I better get x of n out again. So I know that I have that picture. Now the first thing you have to convince yourselves of, and it's not really too hard, I can discuss it briefly on Tuesday, or maybe ask the TAs to mention it in the discussion. But first thing you have to convince yourself is that if S is LTI with impulse response H of n, then its inverse must also be LTI. And the way you check that is you write down the expression for what the property means to be linear and to be LTI, and you just reverse the arrows. That's actually the argument that shows you that the inverse system must also be LTI. So you just have to switch the arrows in those descriptions of those properties. So we know it's LTI, the inverse is LTI, and so it has an impulse response. Let's call it G of n. Well, what did we show about the concatenation? When you concatenate two systems, LTI systems, the overall impulse response is going to be H of n convolved with G of n. But what's the overall impulse response of this system? What system is this if these guys are inverses? It's the identity system, right? X of n goes in, X of n comes out. What's the impulse response of the identity system? Delta of n. Okay? So that proves one direction. That proves that invertibility implies this property. Okay, the third property is causality. So what about when the system is causal? So it turns out that S is causal if and only if, so all of these are necessary and sufficient conditions, if and only if the impulse response is equal to 0. Now, think about it. If it's causal, should the impulse response be 0 for n greater than 0 or n less than 0? Yeah. You want the impulse response to be 0 for n less than 0, because remember, the impulse, it's all zeros. The unit impulse signal is all 0 up until you hit n equals 0. Now, in a causal system, it would be a little bit weird if something you did at n equals 0 affected the output at time n equal minus 10, or in fact, anything less than 0. So that's kind of the way to figure out why it should be that it should be 0 for n less than 0. And then the final property is stability. And so S is stable. Again, it's a necessary and sufficient condition if and only if. And again, all of these properties you can see, they just have to do with the impulse response. They're properties of the impulse response. So here the property is that it has to be what's called absolutely summable, which just means that if you take the magnitude and sum it from minus infinity to infinity, it has to be finite. So this is called absolute summability. And then finally, we have the analogous statements about how the impulse response of an LTI system can tell us about the LTI system properties. And they're completely analogous to what we had before. The continuous time LTI system is memoryless if and only if the impulse response of that system is boring. It's just a scalar times an impulse for some complex scalar A. And so what that really means is that the system is just a gain. Just crank up the volume to some level. The system is invertible if and only if there exists some other signal, which will basically be the impulse response of the inverse system, if there exists g of t such that when you convolve h with g, you get a delta function. So not multiply, but convolve. Okay? And so I'm assuming here the impulse response, of course, is being denoted by h of t. Causality, just as before. The system is causal if and only if the impulse response is 0 for negative time. Right? All the action has to happen after that impulse goes into the system. And then finally, the system is stable if and only if the system satisfies the property that's the continuous time analog of absolute summability. Here it's going to be absolute integrability. So what we need to know is that the integral of the magnitude of that impulse response from minus infinity to infinity is a finite number. So that's the continuous time version, which I think you saw at some point during 45 in some form or other, maybe towards the end of the course rather than towards the beginning and the middle. That's the continuous time analog of everything we did in discrete time.